All right. So Jonathan and I will be talking to you about functions today. So last time, or a couple weeks ago, if you remember, we did a lesson on lines, equations of lines, and this is going to be really related to that. So let's get started. So this is our review for equations of lines. Basically, if you remember, for the lines, you have an x input and a y output. And an example of a line here would be y equals 2x plus 1, where 2 is m, or the slope, and 1 is the y-intercept, 1. And this line, if you remember, if we graph it, it will look something like, look like a straight line. And for every x value, you'll see a y value that we can find. But this time, we're going to be thinking about it a little bit differently. So first of all, thing about a function is it looks, the simplest functions look a lot like a line. So do you want to explain?
So here, this is a pretty basic function here. The only thing that's actually changing here is the 2x. So your input here gets multiplied by 2 and gets added to 1. So what we get here is a line that looks something like this here. And so like Aaron said, this has unlimited solutions. And that's really important because using this one equation, you can solve for any pair of x and y points that'll make this equation true. So we can here fill in some stuff here.
And if you remember, we get these values by plugging in the x values into x in the equation above, and then we find y. So for example, when x equals 0, it'll be 2 times 0, which equals 0, plus 1, which equals 1. So therefore, y equals 1.
Also, before we move on here, this basic line function here, this fits back into the basic slope-intercept form equation, which we learned last time, which was y equals mx plus b. And then we have to remember here, m is slope, and slope is just the change over x over the change over y over change over x. So this is just rise over run. And we can find the slope here, as you can see, going back to this equation here, the slope is 2. We can see that in our line, because if we just get a little section here and we switch colors, if we get a little section of this line, we can count how much change there is in y, just 2, and then for x, there's 1. So going back to this little thing we have here, 2 divided by 1, that gives us 2. And then if we make this even bigger, if we get a bigger section of our line, let's say we go from here all the way up to here, this is 6 for the change in y, we have 3 for the change in x. If you go back to this, our slope remains the same. So that's a review of what we learned a few weeks ago. So let's go back on to today, where we will learn about a little bit more complicated functions.
Okay, so the first thing we're going over is notation. And the definition of notation is just how we write things in math. So it's like a definition. So here we have f parentheses x, and basically what this represents, first of all, it's pronounced f of x, not f times x, because some people might look like see at the parentheses and think it's times, but it's actually pronounced f of x. And it basically means we're plugging in x value into f, which stands for the word function. So instead of y equals 3x plus 1, we can write f of x equals 3x plus 1. And whatever value we want to put x as, we just write that in as f. And we'll see examples of that later.
And so the reason we can choose to write it as f of x here is you can think of everything that we define as f of x as a little machine here. So you can, we can't really see that color. Let me go see something a little bit more clear. You can think of it as a function machine, right? So we have here, and this is f of x. We take a little input here on the top, we plug in x, and then after that, it'll output f of x here, which is, in this case, for this example down here, 3x plus 1. So for whatever we input x, we would multiply by 3 and then add 1. So it's actually the same thing as y here. We're just writing it in a different way. It's for you guys to understand. Okay.
So moving on, let's go into an example with something familiar we've seen before. So we're going to have a line here, or what looks like a line, 2x. And this time, instead of using y, we've used f of x. And we'll see that it basically does the same thing, but f of x allows us to split this into like more complex forms later on. But for now, it's just f of x equals 2x. So the value inside f is what x equals. So for example, if we had 1, which equals 1, so f of 1, that would be plugging in 1 into x. So what we would get for the output is 2 times 1, which equals 2. So if we try it out on this table on the right here, we have a bunch of values here. And first of all, you see that f of 0 equals 0, because if we plug in 0 for x, it would be 2 times 0, which still equals 0. And f of 1 would equal 5, because, oh, wait, never mind, sorry. Oh, yeah. Oh, sorry. To clarify, the table that we're using on the right here is f of x equals 5. It's not f of x equals 2. It's a different function. So again, 1 times 5 equals 5. So that's why f of 1 equals 5. So we're going to try a couple problems here.
So can you guys fill in f of 3 and f of 5 here real quick? So we're going by this equation up here, which is f of 5 equals 5x. You guys can answer through the chat, or you can just feel free to unmute. No, all right, it's okay. So f of 3 here, we're just plugging in 3 for x. 3 times 5, of course, is 15. 5 here, same thing as earlier. 5 times 5, 25. And then here for this question, we're sort of working backwards. So we have our output. We do not have our input. So if you know our function here is 5x, and we know our output equals 40, then we can very easily solve for x, like we learned, I think, a while ago. Just divide both sides by 5, and we get x equals 8. So this here would be f of 8.
And we can, of course, check it by substituting, which means put x back into their function and see if it does give us 40. And if we do put 8 back, it's 5 times 8, which is equal to 40, which means we got the right input.
All right, so does that make sense for everyone? And yeah, Jasper, you were right for 15 and f5. So okay, so let's move on. Hopefully that was all pretty clear.
Okay, so now we're going to do some graphing. So we learned last time how to graph functions of lines. So here we have the function, can you move that up? Yep, the function f of x equals 2x, and we're just going to graph it like before. So if you remember, all we have to do is take 2 points in order to make a line. And we get these 2 points by plugging in points for x. So we just try out values. And we try out values that are easy for us to comprehend. For example, we could try out values like 0 or 1. So in this case, we'll start off with 0. So once f of 0, we can find out what the output is when x equals 0. So if we write out 0 here.
I wrote the wrong. 1 second, sorry. Usually write x here and then by the other side. So plug in 0. So 0 times 2, of course, is also 0. So you can plot that as a point on your graph.
And then we can try out another point, for example, x equals 2. And then we plug that into our function. 2 times 2 equals 4. And we have another point, 2, 4.
So from these 2 points and sort of this pattern here, can you guys sort of figure out the rest of this line?
Like you could try to name a point that would be on this line. Just plug in another value and see what x and y values you get. Or you can try giving us a pair of input outputs. See, 3 and 6. Yeah, that actually works. And we can see this because when x equals 3, 2 times 3 equals 6. So our output would be 6.
So hopefully that was all pretty clear here. This is a pretty easy problem. And then again, we get this line right here. And there is no b here because this goes straight through the origin. So the intercept would be 0.
Yeah, so lines, really easy right now. But later on, we'll see that learning how to graph is very important because we have harder functions. For example, this one. So this was slightly more advanced, the absolute value. And if you did learn this before, just a reminder, absolute value takes the positive value of any number. So if I plug in a negative number into this function, for example, if I put in -2, which means x equals -2, if you put it into absolute value, it'll change the number into 2. So it takes a positive value of any number. And if we do put in a positive number, it keeps it the same.
So you can see here an example for f of x equals x. Here you can see some of the possible values. So for f of -3, what would that output? 1, So for positive 3, right? Pretty simple here. It's a negative value. We get the absolute of this. So that's always gonna be positive. We get 3. Oh, sorry. Let me go back here. So again, the same thing for f of -1, absolute value, we get 1. And then for positive values, 5 here, we get 5. And then working backwards here, it's pretty much the same thing. So what would f of this one be? So if our output here is 10, what would f, what would the question mark there be? Not the absolute value of 10. You're close. Absolute
very,
value
very
of
close.
10 is the function here. So what would we plug in? So what would we plug in for x here?
So another way to think about it is what input would need to go into this function in order for us to get an output of 10.
Anyone else have a guess?
Yeah, this one's a little bit tricky because there's actually 2 answers. And the reason for that is because the definition of absolute value is it takes the positive value of any number, regardless if it's negative or positive. So the answers for this one would be actually -10 and 10, because if we take the absolute value of -10, we get 10. But if we take the negative value of the absolute value of 10, we still get 10.
Oh, my bad.
Well, yeah, the thing about functions is you can only have one output for every single input that you put in. However, there can be multiple inputs that give you the same output, which is important to remember for later on for more advanced functions. But yeah, let's move on. And we're gonna go back to graphing again. Except this time, so if you notice that f of x equals x is still a line. It's just a really simple line. There's no m or b. The slope is just 1. But once we have the absolute value, it changes things up a little bit. So we can use this table to plot points again. So if we try out -5 for this function,
We can, so you guys want to answer some of these points here? So for the inputs and for our outputs.
we'll just do the first one for now. So f of -5, that means we plug in -5 for x, and we put that into our absolute value function, which is f of x equals absolute value of x. So the absolute value of -5 is, of course, 5.
So we can plot that as a point in our graph here. We go to x equals -5 and then go back up. So that's the first point. All right, next, let's do f of -2. Same thing, right? We put -2 into our
Oh,
absolute.
also, if you notice, this graph looks a little bit different because we are including negative x values. So the left side of the graph here, if you can see in the middle of the graph, there's a bold line that indicates the line x equals 0. So that's the middle of the graph. But we also have negative values on the left.
So continuing here down the list, f is 0, of course, the absolute value of 0 is 0. And then going down here, these are both positive values, so remain unchanged. So from here, we can put all the points we found. You see this function is pretty interesting here. Goes back down. Oh, I don't think I can reach that last point. I'll just put something close to it. So this function here actually goes down and dips back up, but this is still a function because passes, so what we call for most functions, a vertical line test. And this is pretty important here. That means that if you draw a vertical line anywhere on the graph, you would only have one intersection. So
this goes back to a point we made on the first slide. For a function, every input value can only have one output value. So if we do a vertical line test where we draw vertical lines down, we can see that
there's
this line only has 1 point hitting it, which means it is in fact a function and it works. So this function is kind of interesting. It looks like a line on each side, but it changes. And the reason for this is because anytime you have an x value, the function changes it so that it becomes positive. So it sort of makes the line, it sort of reflects the line back over so that it's all above the x-axis. So if we move on, so this next one is a little bit more complicated. We have quadratics, and quadratics can get really, really complicated. We're just giving a basic function here. So quadratics are when we have x squared or x times x, which is the definition of squaring something. So a basic quadratic is f of x equals x squared. And the value of inside of x is what x equals, of course. So if we try plugging in points,
same thing here. So as you can see, if we plug in f of 0, 0 squared, so this is just 0 times 0, that gives us an output 0. We do the rest here, you can see it all makes sense. So anyone have a idea for what f of 5 would be for this function? Don't have an idea. So f of 5 here, same thing, we plug it in, we get 5 squared, which is 5 times 5 here. That gives us answer of 25 for this output. And then working backwards here, we have 49. So what would the input for the function be? You guys have it?
this one's a little bit harder because the more complicated we get, the more steps we have to take in order to reverse the function machine, which is finding the input based off the output. But in this case, if the output is 49, that means our input had to have been a number that is the square root of 49. Which, because square root is the opposite of squaring a number. So the square root of 49 right now is 7.
So again, when we're working backwards here, we know that we're looking for a number squared gets our output. So we can just see what number multiplied by itself will give us 49. Here we'll actually see that we have two answers, not just positive 7, because of course 7 times 7 equals 49, but also because negative 7 squared is still 49. So when you have two negative numbers, they multiply each other and it cancels out. You can think of this intuitively. When you have a negative amount of negative numbers, you're going the positive way. So that's why this cancels out. So for this one here, this could actually be f of 7 or f of negative 7. So that'll give you hopefully an idea of what the graph will look like. We'll take a look at that here soon. So does that make sense, everyone? This x squared here? Okay, so I'll assume we're all good.
Okay, so we have more graphing. Now we're going to try graphing this quadratic that we just discovered. So f of x equals x squared. Again, we plot points. We find out what certain outputs would if we put in an input. So right here, I've created -2. So we're going to try that. What happens when we plug in -2 for x? So you guys can try this in at your homes or whatever. Just have it in your head. We're gonna just go through them real quick. So -2 squared is -2 times -2, which equals 4. And -1 squared is -1 times -1, which equals 1. And 0 squared, of course, is 0 times 0, which equals 0. 1 is 1 times 1, which equals 1. And 2 is 2 times 2, which equals 4.
So you see we have the same pattern or a similar pattern that we had earlier in doing absolute value. So you can see that everything here is sort of repeating. And once we graph that, we'll see a little bit more clearly what that looks like. This one should be. Oh, my bad. 1 second. There you go. Erase that one point here. Okay, so we connect this curve a little bit, and you'll see it's something like this.
Now, this is a very special curve. It's not quite a line because it does make sort of a U shape and it bends back in itself. So earlier we saw an absolute value function, but in the middle of it was sort of sharp. If you saw it, it looked like a V. This looks more like a U, and that's because instead of transferring from negative values to positive values immediately, we have a squared. And what the squared does is it works for the smallest numbers possible, and it slowly transforms it from positive to negative, and that's why we see like this smooth transition.
Okay, so does that make sense, everyone here? This is pretty much the same concept. We're just trying different versions of the function machine here. All right, y'all got that? Okay, cool. So I guess we're gonna move on to.
So exponentials. Exponentials are when your input x is an exponent. So that means it's above a number and it's taking the place of what we had earlier. So this sort of looks like the opposite of what we had earlier. Earlier it was x to the power of 2. Now we have 2 to the power of x. And for example, f of 3 means x equals 3. So f of 3 would equal 2 to the third power, which equals 2 times 2 times 2, which equals 8.
So let's just go here. We'll go graph this out for a quick little example here. So this is a little bit more complicated function here, but we'll see sort of the same results. So can you guys try to fill out this table here from what we've learned? So again, same thing. We're just plugging in the values here and just trying to find the output. Yes. So you guys want to give this a shot here? Just trying to fill out this table here.
This is going to be the hardest one we have today. So don't be worried if you can't figure this one out.
Okay, so I'll start us off here with f of 0. So here, let's write it out so we can see this a little bit more clearly. F of 0, we're plugging this in. We replace x with 0, so we'll get 2 to the 0th power. And to the 0th power here, we'll actually just get output of 1. Then we can repeat this for the next one. You have 2 to the first power. 2 to the first power here, just 2. That's it by itself, and we get 2. And then we can continue this pattern. So what do you think is for the next 3 here? I'll give you a little hint for f of 2.
If you're a little bit confused on the first one, anything to the 0th power is 1. That's just a rule of mathematics.
Any questions you guys have too? Feel free to ask us. We can go back to explain anything if you guys need it again.
Okay, so Jasper has an answer for f of 2, f of 3, and f of 4.
So 4, 8, and 16. Yeah, you are correct. So 2 squared, of course, is 4. 2 to the third, 8, and 2 to the fourth is 16. See another pattern here that these are all just being multiplied by 2, and that makes sense intuitively because our function is just 2 to the x. So each time we're just multiplying by another 2. So first one is 2, and then 2 times 2, and then so on. So now we can go ahead to graphing this function. F of 0 we found here is 1, f of 1 is 2, f of 2 is 4, f of 3 here is 8.
And f of 4 is actually so big that it goes off our graph. So if we make an observation here, we can see that this function actually increases our output value very quickly, even though the input value is only going one every time. So different functions change the output by a different value, and it changes like the slope, or what we know as the slope, differently.
Okay, cool. So does that make sense, everyone? This function here?
Draw a line.
Oh yeah, I'll draw a line here so you can see a little bit more clearly. And how because this line here is not a straight line, this is a curve, we can't have a slope for it because the slope is ever changing. And when you get into calculus, a little bit more about that, but for now, we're going to leave it there. So now that we've gotten all the basics of functions, we're going to do some more stuff graphing in Desmos. So before we do that, let's do
an example that's very relevant to our daily life, actually. So it's about the curve that a ball travels through the air with. So let's say Aaron and Jonathan are playing catch. Aaron throws the ball to Jonathan, and the ball follows the path f of x equals negative x squared plus 9. Now, this function looks a little bit different, but it's actually just a quadratic, which is where we square x. And we changed it a little bit. We added 9, and we took the negative value of it. And we'll see how this changes the function later on. But if Aaron is standing at point -30 and Jonathan is standing at the point 40, can Jonathan catch the ball? Which means, does this curve go through Jonathan's point?
So again, here, I'm going to draw out some of the stuff. Aaron is standing at -30. Jonathan is standing at 40. So here's where they're standing. And now let's go fill out our chart here, our little table here for input and output. So do you guys have an idea of how we can do this? Yeah, same concept as earlier. We just want to find some x and y values so we can plot some points on here to get an idea of what our function looks like. So anyone want to give this a shot? So let's start off by coming up with what inputs would make sense for solving this problem here. Anyone have a guess in the chat?
Usually you want to start out with easy values like 0 and 1.
One? Yeah, 1 is a good starting point, right? Because 1 here is within where Aaron and Jonathan are standing. So let's plug in f of 1. So we can fill out our little function here, right? So what's f of 1? It's negative. We switch the x out for 1. 1 squared plus 9. And that gives us 1 squared. And then by order of operations, we do the squared first. We get 1, and we get that negative. So 9 minus 1 equals 8. So at 1, this ball is here. All right, cool. It's a good starting point. So what other points can we do? You have another guess? All right, so we can do many more points in between where Aaron and Jonathan are standing, right? And that would give us a look at what the shape of this graph is. But we can go back to think about what the problem is asking us. And it's asking us, can Jonathan catch the ball? So what that really is saying is, does this graph here, this line, or this curve really, does this pass through the point 4, 0? So if we want to see that, what do we actually have to check? So what's the one point we have to check to solve this problem? Anyone have a guess for that? Jasper, Joyce, you got anything? No? Okay, so well, actually, to solve this problem, all I have to do is check, and we just have to plug in f of 4, right? So you can check f of 4, and if f of 4 makes sense for this problem to be on the line, then we'll see what it is. So let's plug in f of 4, same thing, negative 4 squared plus 9. And we can do order of operations again. 4 squared is 16, make that negative, and then plus 9. Now actually see that this gives us a negative value, right? So 9 minus 16 is obviously going to be negative, and you can figure this out here. This is going to be negative 7. This will be negative 7.
So when the ball is at an input value of 4, it actually gives an output of negative 7. And negative 7 obviously does not equal 0, which is where Jonathan is. So Jonathan cannot actually catch the ball. And
yeah, so if you think about it at negative 4 here, what's really saying is that the ball would be 7 units down into the ground here. And of course, that can't be possible, right? But saying that if the ground wasn't here and the ball kept falling, according to this curve, it would be at negative 7. So we know that isn't true. But now that we've solved the problem, we can still do a few more points here to figure out the curve of this line. So again, the 9 here, what this tells us is that when x equals 0, the intercept will be at 9. So we can already put a point there. And then based off what we have here, we know this is a quadratic, right? We know that quadratic mirrors. And because we didn't shift this left or right, we can just mirror this side here. And then again, we can continue on line, so we can do sort of input of 2. So I can find where my pen is. We go f of 2, negative 2 squared plus 9. Order of operations again, same thing. 9 minus 4, and that gives us value 5. So now that we know here, we can again mirror this to the other side. And now based off these points, we can sort of figure out where the ball is, right? And again, so I'm not going to do f of 3, but f of 3 is on this line here. Because Aaron threw the ball, so of course it started from there. Then you just follow this curve around. We'll see it's something like this. So now we can see that Jonathan obviously could not catch that ball.
And if we did continue the line, we would see that when f equals 4, it does go down.
And Jasper, you asked that, how do you know what the x is? Do you just guess? So again, when we're checking for if Jonathan could catch the ball, we just want to check if the line hits where Jonathan is standing, right? So we just plugged in where Jonathan is standing. We knew that Jonathan was at x equals 4 because he was at the point 4, 0. And then the other points that we plugged in, we were just plugging them in somewhere between where Aaron and Jonathan were standing because we wanted to figure out what this curve was going to look like.
We also know that it's completely possible to have outputs between where Aaron and Jonathan are standing because one of the rules of functions is that it has unlimited values and it has unlimited points that it works for, which means for any x value, well, at least for now, for any x value, we will get a y value output, which means that we can test any point between Aaron and Jonathan, and we get a point that will help us find what our graph looks like.
So does that make a little bit more sense, Janser? Yeah. Okay, cool. So
okay, that's all we have on this slide, but we'll actually move to a graphing calculator, and that'll help us look at these functions a lot easier because a graphing calculator is obviously smarter than a human.
Okay, so now we're going to be going over to explain a little bit of graph theory here. Oh, let me clear the annotations. Sorry about that. Okay, so again, going back to look at that example that we had earlier, you can just graph it here. Fx, oh, don't like that. F of x equals negative x squared plus 9. Oh, something else popped out. Okay, so here's the path of the ball as we find it. So we can see that Aaron threw it. He threw it pretty high up, went up, and then came back down, and it was not far enough for Jonathan to catch. And then when we plugged in x equals 4, you see that ball is actually way down here or around down here. So there's no way he would have caught that. So why is this graph like this, right? So when we went over earlier, when we only looked at f of x equals x squared, we found that it was facing upwards, right? And it was centered right here, nice and neat. But why is this function sort of moved up and pointing downwards? So we can go look at a few different things. So first of all, I'm going to get rid of the 9. So we'll get rid of this example. Oh, sorry for that zoom. Zoom in a little bit. So we'll look at these two functions here. The black line is negative x squared, which is sort of like the function that we had from the example. And then the red line here is x squared. So x squared is our original, and we can see how the black line is reflected down. So why is that? It's because we have the little negative here, right? So for every output of fx equals x squared, actually, this will make a little bit more sense. We change the name. We don't have to have x, we can name it other letters. So if we have all these outputs here, which are positive because it's x squared, and we make them negative by putting a negative sign in front of here, it'll make sense that everything is below the x-axis, right? They're all pointing downwards. So does that part make sense, everyone?
So right now we're sort of getting into the translations of functions, which is something that can be very, very variant because there's a lot of things you can do with a function. The ones that we discussed today were just very basic. We call them the parent equations, and that's because they're the most basic. And the other equations that we have that we make from translations, such as adding a negative in front, that flips it. We also added another one in the problem.
Yeah, so we'll get to a little bit more of the important translations later. So does everyone get how this black line here is facing downwards compared to the original function here, which is g of x equals x squared? Does that make sense to everyone? Again, the g of x versus f of x doesn't matter. The letter in front is just for naming purposes. And usually we go by fx, but since there's two functions here, we're changing them around. Okay, so now continuing to get this fx here back to the one example. So the one example was moved up a lot, right? So you can think of it intuitively as pretty much every single point on this line just being moved up by a certain amount. So you can do that pretty easily just by, again, as we saw in the function, adding 9 to it. So what it just does is for every output of x negative x squared, we just add 9 to it. So everything gets shifted up 9. And that's how we have this little graph here. And again, we've already figured out how to flip graphs, right? From going upwards to downwards, that's just adding a negative here in front of the x. And then shifting it upwards and downwards is just adding a separate constant here, right? 9 will never change, it's always 9. We can add that to the end. So now we're going to go over a little bit about moving the functions left to right. So what we would do there, so you can add a little parentheses, start adding stuff to x. So I'm going to make a copy this function. Again, for naming purposes, call it something else. We'll call it h of x for now. So right now it's in the middle, right? But if I add something to it here, we can see that it moves over. So for when we're adding stuff to the x here before we square it, again, adding stuff moves it to the left, subtracting it moves to the right. So you have to think of it sort of counterintuitively. But knowing these basic changes will allow us to draw quadratics pretty much wherever we want. Right, so we can move now up, down, left, right, and flipping. So does that make sense here for why we're adding stuff here? We're just shifting every input value over. That's what we're doing here by adding 1 to x. So does that make sense, everyone? Again, any questions you guys have, feel free to ask in the chat. So Okay, so looks like we're good. So now let's talk about one more thing that we can do to quadratics here, and that's squishing them or stretching them out. So well, we can do that by adding a value in front of here, in front of the x squared, or what we're doing to the x. So to stretch a function out, we can put a number that's bigger than 1. Right, so that'll just stretch the whole function out. See, it's a little bit more squished. And if you want to squish the function, compress it a little bit, you can just put a value less than 1, 0 0.5, 0 0.25, and even 0 0.1. So there are all the basic translations for the quadratic functions here, and that should allow you to draw a quadratic function wherever you want, anywhere on the graph. So we can go over a few more examples. So let's see, I'll write a new function here. I'll just write, let's name it f of x again. So let's say I do 6 x minus 4 squared minus 3. So just by looking at this new function here, let's hide all the other ones for now. Let's not make Desmos too messy. Just looking at this green function here, just looking at this number, what can we tell from this based off what we already learned earlier? So first of all, let's go over which way is the graph opening up. So which way is it sort of facing?
Oh, and just as reference, here's our normal equation, just the basic one. So x squared.
So you want to answer that in the chat, or you can unmute. So first of all, looking at this equation here, you can also look at the graph that'll help you. Which way does the mouth open up for this quadratic? This quadratic opens up, right? So we, as you can see, we're looking past the squared part. We don't have any negative signs. So that means all the inputs that we had were squared and made positive. But then we can see something peculiar, right? Even though it's supposed to be all positive, we can see some negative values here. As you can see down here, there are many negative values. So why is that? Does anyone have a guess here? So this is just building on what we talked about earlier from the vertical shifts. So can you guys try to figure out why we'd have negative values, even though this is supposedly positive here? No? Okay, it's okay. This is probably might be a little bit difficult. So remember when we talked about this end here, right? This is shifting every single point on the line. So if I just get rid of this for now, we have the green line, right? And whatever we add to the end, we're shifting every single point on that line by that much. So the -3 here means we're subtracting from the y value, the vertical value, 3 for every single point. So where this normally would be 0, for 0, we can see we have 4 -3. And then where we have this number, that's a pretty nasty number there, where that is 0, that would normally be 3.293 and then 3. So does that make sense? I've already broken down the main parts. Opening up, we've shifted it down by 3 units. Okay, now what? So obviously it's not centered, right? So we can look at the middle of this quadratic here. You see, what's that middle point? The middle point is at x equals 4. So how did we get there? Look back to the original equation. What do you guys think? Guys have any guesses?
Okay, if not, remember we changed 4 things about the graph. One thing is the negative value that we put in front of x. Another thing is the number that we put in front of x. So that was 6 in this case. The third thing was -3, which moves the function up and down. And the last thing, if you remember, is the number we have inside the parentheses, which is behind x. And that moves the function left and right. So in this case, the point that we were looking at was this point 4, -3. And we were looking at why it moved 4 times to the right instead of staying at 0, -3. And this reason is because we have this -4 behind x. So every value that we change, it's subtracted by 4. And this is sort of counterintuitive. But basically what this means is that the y value hits x equals -4 4 times faster, or not 4 times faster, but 4 values before normally. And that's why we have this result.
So if that didn't really make too much sense for you, you can just remember that this is counterintuitive. So subtracting it will move it positively in the graph here. So moving to the right here, and then adding it will move it to the left. So we can see why the center of this graph here is normally where we'd be on 0. As you can see from our parent function x squared, it's now at 4 because of the minus. And lastly, we can see that compared to our parent function here, this green line, this is a lot thinner, right? It looks a lot stretched out. So why is that? It's because we multiplied the whole quadratic here by 6. Remember, any factor that you multiply here that's greater than 1 will stretch out the graph, and everything that's less than 1 will compress the graph. So hopefully that made sense. Again, guys, any questions that you have, please feel free to ask them. You know, we barely, it's only 2 of you guys here, so it'd be great if we can do our best to help you all understand this concept. And it's totally okay if you don't fully understand. This is some of the harder stuff for graphs. So any questions? Ask them in the chat if you want to clarify anything. No? Okay, so we'll do another practice problem. So, well, so now we're gonna do one more. And I'll hide this green one here. We can keep our parent function as a reference. This time, I'm gonna hide the graph and see if we can figure out the same thing. So we draw out the graph. Okay, so we're not going to be able to figure out exact values. That'd be pretty difficult. You have to take your time to write a table. But just from looking at this function, what are some basic things that we can already tell just by looking at this equation here? Again, there's the 4 basic things. Which direction is it facing? How far up and down has it shifted? How far left or right has it shifted? And is it being squished or is it being stretched? So just looking at this here, can you guys sort of tell? Jasper, Joyce, you got anything? Confusing? So which part is confusing? Just let us know. We can go back to re-explain it in a different way if that would help you.
Is it this function specifically, or was it any of the values that we were changing earlier?
So just this function in particular. Okay, so we'll break it down. So let me make a few copies of this here. We can see sort of how we got to this point. So again, we always start from our parent function here, x squared, right? And we can just go down the line. So from the parent function, we first, let's say we first did the stretch here, or the squish in this case, which is multiplying it by 1/2. So does this part make sense to you? Let me change this to a different color. So the original is the red line, and the blue line here is a little bit wider because we squished it down. And you can see the only difference between these two here is that I've multiplied this one by 1/2. And again, this value is smaller than 1, so it'll sort of squish the graph. It'll bring it a little bit wider. So does that part make sense? Yeah, good. All right, cool. So the next step of this, let me write this function again. Now, let's say we're going to move it vertically. Oh, wrong number. So let me change the color again. I have them all in different colors. So going down the line, we first started the red, now we're going to the blue. Now we're at the green. So you can see this green one here, sort of higher up. So do you understand why that is true? It's because the only difference here, again, we're adding 5 to it. So for every single point on this blue line, we're just moving it up. So if I draw a line here, just a vertical line, let's say x equals 1, we hide our parent function. we can see on the blue line here, this point was at 1, 0.5. But on the green one, because we added 5 to that point, it's at 1, 5.5. So this point has been shifted up 5 units, and it's the same for every single unit on this line, every single point on this line. So that's why the whole thing is just moved up. Does that make sense? As you can see, if we move this black line here, oh, that's not a very good number, but this is 5.72. So if we go down here, we can expect on the blue line for this to be 0.72. And you can see that is the case. So does that make sense? The adding 5 part here. Yeah, all right, cool. So we're almost there. Just got one more section left. Let's do this. Rewrite this one more time. If I can write it correctly. Now we have x plus 2 squared. So I'll get rid of this black line here, and I'll replace it with y equals 1, and we'll go switch around some of the colors. Okay, so this is getting kind of messy. I'll delete some of the earlier versions. So now we're only left with the final function, right? So we saw, remember how we got to the green one, right? But now you can see the difference between the green one and the orange one is x plus 2. And now on the orange one, it's been shifted left. So let's move this line up here. Let's say, let's give it a nice number. Oh, here. So on the blue, we can see, oh, it's not a very nice number here. It's also not very nice, but let's just deal with it for now. This is negative 2.324 for the x value, right? And if we look over here, this should be negative 4.324, right? Because we're moving it to the left 2 points. So remember, the part in here, this is counterintuitive. Adding numbers to it will make the graph go left, and the subtracting numbers from it will make the back graph go right. So subtracting makes it go the positive direction, adding makes it go in the negative direction. So you can see the difference between these 2 points here. It's just 2, and we're subtracting 2. We go from negative 2 point something to negative 4 point something. And that's how we reach our final destination for this graph. So does that make sense? Start from x squared here, our parent function. We squished it down a little bit, moved it up, and then scooched it over. So that's how we got from this red line here to this orange line. So does that make a little bit more sense? Hopefully. So yeah, that's a pretty basic and quick introduction to some graph theory and parent functions. So I know this week has been pretty confusing. Well, for the discussion problems this week, most likely will be more similar to some practice problems. We'll continue to do a detailed review of this next week and hopefully go into some more interesting functions here. So yeah, pretty much it for today. We're gonna end class 4 minutes early, or in Math Circle, I guess. So thanks for coming. I know that wasn't a very easy lesson. We went through things pretty quickly, but this should give you a head start or for a lot of the harder concepts you guys are going to learn soon. So yeah, that's it. Thank you guys. Thank you guys. And we'll publish this on the website, the link to the Desmos calculator with these functions, and we'll have the slides available as well on our website and in the Discord. Yeah, thank you. You guys can leave now. Okay, Joyce, did you understand all the concepts here? Is there any questions right now? You can feel free to ask them.